Good morning, fellow students. Today we're going to talk about simulation, a student's perspective on the art of prediction. So, what is simulation? Simulation is the process of mapping real-world scenarios into various systems and models over time. There are three different categorization perspectives for simulation. Within each perspective, there are two opposing kinds of simulations. First, we have physical models versus analytical models. Physical models are tangible, mostly performed in a laboratory environment with concrete objects like hardware. Analytical models, on the other hand, are usually performed through estimations and with the help of specialized software. The next perspective is discrete versus continuous models. Discrete are models that use variables at a specific and instantaneous point in time. Continuous state variables can change constantly over time, described by differential equations that are solved numerically. The final perspective is stochastic versus deterministic. Stochastic uses random inputs to find real variation in outputs. Deterministic focuses on always keeping the same inputs and outputs. The first thing that comes to mind when we think about probability simulations are rolling a die and flipping a coin scenarios. But we virtually use software that performs simulations every day. Some of the most common ones are estimation of waiting times, be it you have to wait for the metro or bus to arrive, or simply waiting times in lines, like when you're trying to get in Space Mountain and it says you have 2 hours to go. Bummer. We have also video games that model real life occurrences pretty accurately. Stock markets are simulations, fashion design applications, among many others. An early physical simulation was the use of wooden horses to practice riding before battles during World War I. Simulations have been developed greatly, with the implementation of software and hardware to accurately replicate real-world occurrences. Nowadays, pilots at the beginning of the training spend countless hours in simulators before flying an actual plane. People can also learn how to drive through simulators, and automakers can inspect cars' aerodynamics by simulating wind resistance. Also, meteorologists can model weather behavior for weeks ahead. Now we have a little video that shows a simulation of muscle movement through software.
The system corrects itself through multiple trials to make the model walk.
Fascinating. As we have seen, simulations have many advantages, such as there are no defined limits, so the model can give you results that are not experimentally measurable with our current level of technology. It can also be run many times to explore alternatives such as failure scenarios without exhausting resources. And the only limits are your imagination, your programming skills, and your CPU/GPU. Simulations provide practical feedback without the risk involved with building the actual system. On the other hand, there are some disadvantages in simulating actual system, such as the verification process. The credibility of the developers might be questionable, as well as the quality of their assumptions. Also, it is hard to verify effectiveness of simulation when developing a model based on statistical estimates and uncertainties. And there's also simulation errors, such as input errors or program malfunction. So another term you hear a lot when referring to simulation is probability. Probability is the likeliness of an event happening. So, since simulation is a modeling process, probabilities help account for all the possible scenarios and happenings in a real-world system. In relation to probability, there are probabilistic distributions and functions that generate values that best fit a given model. The two main functions we utilize are the probability density function, which is PDF, versus the cumulative distribution function, or CDF. In the next few slides, we're going to see some videos depicting various simulations, starting with very basic Excel models utilizing the random function, following two types of computer software, Java and Simio. So recall that engineering analysis, or APSC 3115 final project, in which we had to model the financial viability of installing water pumps with various volumes for a water supply company. So here we have the volume, which is 2 kiloliters, I believe, and the revenues depends on water demand, which was modeled by the inverse normal function of probability simulated by the random function right here. In the other hand, we have costs, which are dependent on the arrival time of the water, and these were calculated or simulated with the inverse exponential distribution. Here's the formula, and the probabilities were simulated too with the random function over here. Also, in engineering economy, or Dr. Shitu's class, we had to model also the financial viability of a geothermal plant. So we had to calculate all the cash flows, revenues, and allocation costs to calculate the break-even price over here of the electricity. We got this value by simulating a scenario in which there would be no profits, so we used GoalSeek to find the electricity price that would equate revenues to total costs and expenses.
This is an example showing how Excel can be used for simulation. In this instance, we apply the probability and statistics to best fit a model when rolling a die for the Monte Carlo simulation. That means by using a random sample to evaluate data, you can see what-if scenarios. It is a technique used to understand the impact of risk and uncertainty. A simple die has 6 sides with numbers 1 through 6 on each of the faces. This means that whenever rolling a die, for example, there is a 1/6 chance or a 16.67% chance that when you roll, a 5 will appear on the die. 5 is an arbitrarily chosen value of the die. In this Excel file, we utilize the rand function to help generate random values from 0 to 1 over a uniform distribution as mentioned earlier. This probability distribution refers to a distribution of random values that may occur equally. As you can see in the upper left-hand corner, there are broken down percentages in relation to each face of the die. For example, when generating a random number of 0 to 0.1667, a 1 will appear, and this continues all the way up to a random number generated up to 0.8333 and below 1 when a 6 will appear. On this table, I utilized a VLOOKUP function to look up to return a value for the outcome. Below, there's a die sampler that shows the uniform distribution being set at 0.8 with a die outcome of 5. In the data table, there are 60 rolls performed for one die, and 60 corresponding rand functions that will generate a value over the uniform distribution and respond with a certain amount of appearances for each face of the die. For this run, there are 11 appearances of 1, and so on and so forth. You would expect that over 60 times of rolling a dice, there would be an equal turnout for each face of the die. This is not the case this time because this is a random distribution. This Excel simulation exhibits a major advantage associated with simulation. We are able to roll a die 60 times instantaneously without having to waste any time, and we could continue to generate values even up to 1,000 times.
So this is the zombie simulator that we've made. I'm going to take you through the subclasses just to get an idea of how the randomization functions are used in each one of the situations above. So first we're going to have a GUI pop up, and it's going to have a bunch of buildings randomly spawned in. We choose in Zombie Sim the number of buildings, which is set at 12 right now, and then this building block will randomly spawn them in into different places on the graphical user interface. In the human class, we spawn in white dots, and they are random in the sense that they'll move in whichever direction they choose until they see a zombie, and their goal is to run away. So the second they see one, they'll turn in the opposite direction. Zombies obviously have the opposite effect, and whenever they see a human, they'll stick towards that direction, or they'll speed up a little bit, but that's also random. Also in the human class, we have a random function at the bottom which has to do with immunity. So once in a while, an immune human will spawn as blue, and if that person touches a zombie, he'll become a human again to kind of level the playing field. But since it's more rare, it doesn't spawn in as often. So here's the program running. We have these 3 zombies now multiplying. Here is the immune human in blue, which just turned 1 back to a human, and this is how it works. It just spreads as fastly as possible, and as you see, almost everyone is now a zombie. So I'm going to pause this, and if you take a look on the right on the console, this is just the initial spawn in, which it lets us know that somebody is immune, and it gives us all the information of that initial drop of everything, which is all the positioning of the buildings, the humans, and the zombies. So you can see the buildings as X's, the walkable areas as dots, H being the humans, and if we look around, we might find the zombie, which is right here. Here it is. So that's basically it. That's how it works. It's a pretty fun simulation. You'll run it again and again, and each time it'll be different. So new building setup, actually no immune people this time. Fun program, easy to use, good for simulations.
This is a simplified simulation of a hospital using software called Simia. There are 4 different patient types in this model. They're routine, which is colored white, moderate is green, severe is yellow, and urgent is red, each with increasing priority. Although it is not displayed in this video, every feature in this model is based upon statistics and data collected. Each patient type has a different type of treatment time, distribution, and sequence. For example, urgent patients in the color red will have the highest priority, therefore they also have the longest treatment time distribution that lasts anywhere between 10 and 55 minutes. Urgent patients will also go through a sequence different from other patients, going through a trauma room and then after signing in. They skip registration. As you can see, the red figure follows that path. Each server has a different capacity and it will have a different processing time for distribution for each type of patient. For example, exam rooms, you will see the middle server with a capacity of 3 people, and it treats different types of patients along with corresponding treatment times. You can see that these white routine patients entering, signing in, registering, then going to the exam room.
So a little summary of our presentation. Simulation is a great way to model different systems without wasting too much time nor money. Statistical probability can be applied to enhance data and knowledge. And there are different types of simulation software, from Excel to Simio and even Java code. If you have any question, please address them to the 4 handsome gentlemen presenting this video. Thank you very much.